So we will, for the next 1 hour, 30 minutes, we will be discussing, we will be giving a short overview and kind of safety management in projects aspects for next 1 hour, 30 minutes. And especially this presentations goes in a kind of a flow. So, and the presentation will be shared between me and Supriya. So we will be just exchanging the slides in between. Yeah. So, and since so I would like to start with Continental first. Yeah. So Continental is having a vision. The vision is your mobility, your freedom, and our signature. So highly developed intelligent technologies for mobility, transport, and processing make up for the world. We want to provide the best solution for each of our customers in each of our markets. And this is how we satisfy the demand of our stakeholders and become recognized as a highly reliable and respected partner, creating the highest possible value. And that is about our vision. Yeah. And let us just look into the Continental's core technologies enabling the mobility. Let us just have a short retrospect. So from 1886 to 2016, so 1886 was the first motor wagon. This is the first car produced by Carl Benz. And in 1900, there were only 9,500 vehicles all over the world. Yeah, all over the world, only 9,500 vehicles. Now in 2016, when you take, I think you can just see the numbers here. So we could say that individual mobility is a success story. Let us just see that for the future, will the individual mobility will be a success for the future? So what are the pros and cons? So pros is that we have fun in driving. We have private space, especially in the time of Corona, right? Actually, we don't want to have social contact, so that it ensures a private space. It ensures the freedom to drive. And then what are the cons? So a lot of cons is pollution is one biggest problem. Boredom is a problem. Waste of time, stress, crashes. So now we have, we are more talking about safety, right? So let us talk about the crashes. The future of individual mobility can be a success story by looking into these figures. 1.25 million traffic accident fatalities worldwide. And it is expected to increase. The United Nations goal of the decade road safety is that to save 5 million lives. And this is what we are going ahead. So there is a motivation behind for moving for the safety system. Yeah? So we have to reduce these fatalities for the future. Then, by looking to these topics of individual mobility, Continental has set our megatrends. So Continental have for safe mobility, for clean power, for intelligent driving, for global mobility. So let us just, since the topic is with respect to safety, let us go with the safe mobility. Let's talk about safety. Reduce the number of fatalities and those injured. 1.25 million people die in road accidents every year. A further of 50 million are getting injured. And when you just look into 9.3, 19.9 million, 17.3 million. So these are the statistics from all the worldwide regions. Yeah. Now, safe mobility, what could be the crash causes? 95% of all road accidents involve some human error. In 76% of the cases, the human is solely to blame, and misjudging driving dynamics, weather 50%. Distraction constitute 38%, 39% of passengers will, and 26% of truck do not activate brakes before a collision. Some 40% more do not brake effectively. So maybe the main reasons could be underlying causes could be alcohol, inexperience, tiredness. So all these things, distractions and all are caused by the inexperience that people are not experienced how to drive on the road. So how we can handle it? How to bring down traffic fatalities? We have 4E, education, enforcement, engineering, and environment. We are into engineering, yeah? So we had to find solutions in engineering. So we will focus on engineering. Let us just get into a broad picture of mobility. Mobility has different aspects. Hello. Yeah. So safety, comfort, and dynamics. Safety is in all situations. Comfort is arrive relaxed, and we enjoy the driving by the vehicle dynamics. And we achieve the safety aspects by sense, plan, and act. That is, sense the environment, planning the action, and acting by using the car's control. So these are the products like for sensing. We sense with the sensors, we plan with the controllers, and we act with the actuators. Just to rate an example for safety, emergency brake assist or electronic brake system, adaptive cruise control for comfort, and dynamics is torque vectoring. And now we know, now we see that the safety is an important part. Safety have its own place for the future. And when we, as a product company, our product development has to follow the state of the art. And how we follow the state of the art. What is our motivation for product safety? Product safety has been always an important topic, not now, even before. There are Act on Liability for Defective Products, Product Liability Act, Act on Making Products Available on the Market, so Product Safety Acts. This has been there for since many years. Now, together, product safety, so the standards, we have to adhere to the standards related to the design and manufacturing of the products to ensure they do not cause harm or hazards to the customers. And how to achieve it, and what is the new standard that we had to align our architecture with? So that is like the state of the art ISO 26262, which defines the process, defines the architecture, and defines the method how to achieve. Let us know the standard ISO 26262. So Supriya will take you through the structure and the standard of ISO 26262. Supriya?
Yes, thank you, Prasneh. So, a small overview on the ISO 26262. Officially, the ISO 26262 was first released in November 2011, and later we had a second update in the 2018. So our ISO 26262 was derived from IEC 61508, which is a mother standard for all functional safety, and we have taken to our automotive needs, wherein we have it for the transportation domain, the mass production, and the distributed developments. So for the representation of the state of art means we have to follow the national or international norms in order to implement the best technical solution. And this is applicable for the series production of passenger cars with all weights, trucks and buses and motorcycles. And we also have it applicable for the safety related systems and the electrical or electronic systems and onboard the vehicles, including their embedded software. Yeah, moving on. So these are the parts of the ISO 26262. Initially, in the first version, we had 10 parts, but now in the recent 2018 updated version, we have 12 parts, wherein the first part is about the vocabulary. Here in the vocabulary, all the terminologies that are mentioned in all the parts, the meaning of that will be present in the vocabulary. And part 2 is describing the management activities of the functional safety, and part 3 we have the concept phase, and later we move on to the development phase from the part 4, wherein part 4 is for the development at the system level, and then part 5 we move on to the hardware level, and 6 again we have the development in the software level. Then after this again we'll be moving on to the production, that is the part 7, and in part 8 we have the supporting process, and 9 is about the ASIL oriented and safety oriented analysis. Part 10 we have the guidelines on ISO 26262, and part 11 is the guidelines for ISO 26262 to semiconductors, and for part 12 we have the adaptation to the motorcycles. So under the elementals we have our part 1, part 9 and part 10. Under the management activities we have our part 2 and part 8. Next, for the development activities we have a part 3, 4, 5, 6, 11 and 12. And next for the operation we have a part 7. So this was a in the new edition of the ISO 26262, as I said, part 11 and part 12 were added. So this was a short overview on the ISO 26262. So how we are adapting it to the V model, Prashneh will be taking us through.
Okay. So we do have our conventional development, and we had to, as Rani has, I think, mentioned at the time of introduction, that we have to incorporate the safety cycle into the V model. You know? So it has to be, then only we could make it possible. We cannot go in parallel. So let us just go and see how the safety cycle has been placed. Okay, so what is the safety life cycle? So what the safety ISO 26262 defines planning, methods, technical design, processes, and culture. So then it has to be integrated into requirements and architecture, then safety analysis and test. So basically, we have to do a good adaptation on methods, process, tools, and work products. So going to the safe cycle. So we have we have the item definition, then and hazard analysis, and deriving a functional safety concept at the concept phase. And then we have product development, the planning of the system technically. Developing the system technically, planning for that, and also developing the components for the system, integrating, testing, and releasing for production. And after SOP, that production and operation and service and decommissioning. So this is an overall view of the safety cycle. So now we do have two things, like one is production and one is development. So let us just first focus on development. So product concept and development. We would like to integrate this into our normal development model. So if you want to make a company culture within which could adhere to the functional safety, definitely we have to take this cycle, we have to make it into an integral part of our development, which we cannot differentiate, or we don't run parallel processes for functional safety and so for the development. So like, let us just give a V cycle, FSM in V cycle and FSM and systems engineering. Let's just look into the basic aspects of system engineering. So system engineering is a domain which defines systematic approaches, development of complex systems, and address all aspects of system within its life cycle. So when we talk about V model was published in 1979, mainly motivated by software development, and it defines the development phases. I hope everybody is aware about it. And functional safety requires a systematic approach of development to mitigate the risk. So let's see. On the bottom x-axis is the time, and then on the y-axis is the development from the components, and the components integrated to become system. System is integrated into vehicle. So we have requirements flowing from the vehicle level towards the component, and we implement the component, integrate, test, and validate up to the vehicle level. So this is what, in simple, it is going on. So let us see what is a normal process of system development. We have item definition. We define the item for the system. Then we derive the functional requirements. Then we make functional architecture. Then project plan. Once the function architecture requirements are clear and is aligned to the vehicle architecture, then we define, we could start our system development by planning. Then we make technical requirements, then going to the system architecture, then requirements for the components and architecture for the components, defining the test concept at all levels, then executing the test at component level, system level, and completing this V model. So what is the difference between functional safety when we integrate? So when we integrate functional safety, so we have a development interface agreement, that is the supplier and the OEM is agreeing that we have to adhere to functional safety. And we are agreeing by evidencing the compliance by giving the work products at each phase. Which all work products has to be made is clearly defined and agreed between both the parties here. Then we do an impact analysis. Okay, there is a system requirements, there is a functional requirements which has been came that has to be realized against a product. Then we do this risk analysis. We say that hazard analysis and derive the safety goal. And once the safety goal is being defined for the vehicle level, the safety goal has to be aligned to the functional requirements from the system. And once there is a mutual understanding about the functional requirements for the vehicle from the system, everything is proper. So then we do clearly make the safety concept, which have the clear functional safety requirements, safety architecture. Okay, then that side means like that phase of concept for for a system which we can give a defined set of functions is already made. Now we can really start with the development by the planning. So then when we take into the safety requirements and safety architecture, whether our existing architecture of the system is in line to the safety requirements. That is what the next step. That is how we derive the technical safety concept. So technical safety concept, we will be having technical safety requirements and technical safety system architecture. We do analysis after this to ensure that whether the system has achieved the defined metrics or by ISO 26262. on the safety relevant functionality. We refine, we iterate, we refine the architecture if it is not met. Then once it's freezed, so now the system block is ready with all the sub component blocks. Now each components has to be developed based on the technical safety concept requirements defined by the system. So the requirements, the component level requirements are derived from the technical safety requirements of the system. Then we do the design FMEA, the analysis at the design level, ensure that the metrics is being covered. And then going with the same process, test process concept for the system and test concept for all the components, and finally validating. And final topic is that once we finish all the testing validation, then we at the end of the cycle, we document all the evidences inside a in the safety case. So the safety case, finally, it could be delivered to the customer as agreed. And we have to ensure that the process, what we have set, is in compliance with ISO 26262. Thereby, we have to do the necessary FSM reviews. FSM 0 is review is for the concept, 1 for the design, 2 for the test concept, 3 for the test outcome, and 4 for the consolidated safety evidences documented. After this, let us start defining boundaries and entering into an agreement with the OEM, the supplier and the OEM. So let us say define as item. So item definition defines and describes the item, its dependencies on, and interaction with the environment and other items. Supports an adequate understanding of the items so that the activities in subsequent phases can be performed. So who is responsible? The system requirements engineer, and could be supported by the system architect, and the information could be shared by the safety manager. And who takes care of just giving an example of a small item definition. So it's an electronic brake system. So we have actuations, power supply, combustion, all the environments there. We have a wheel speed sensor input, wheel brake outputs. So a kind of small example of the item definition. Now we have to enter into the development interface agreement with the customer. Supriya will be explaining it in the detailed way.
Okay, so now that we have our item definition ready, we'll be moving on to the development interface agreement. So as the name itself says, it is an agreement or a contract that is made between the two parties. Now, who are these two parties? Is the OEM and the supplier. So the safety manager from the OEM and the safety manager from the supplier, they sit together and discuss and come to an agreement that what has to be done. Now, what is inside the development interface agreement? Can you move on to the next slide? Yeah. So here we have to take care of three things. First is that, is the work product required to be performed? Second is who does what? And third is how are we going to deliver this particular work product? So initially, for the first question, is the work product required to be performed? Can you move one slide further? Yeah. So here we have three terminologies, that is the mandatory work products, the recommended work products, and the optional work products. So based on the ASIL level, our ISO 26262 defines it saying that there are work products that have to be mandatorily performed, and some work products are recommended to perform, and some work products are optionally optional to perform. So you have to discuss with the OEM, sit together and discuss. All the mandatory work products, you have to obviously perform it and deliver to your OEM. For the optional work products, you have to sit and discuss with them, and you have to finalize whether they want us to do it or whether they don't want us to do it. Are we doing it or not? So we'll put a Y or N in here, whether we are doing it or not. So next is who does what. So for this, we'll be following this RASI chart. This RASI chart wherein we have RASI. R is for the responsible person who will be conducting the activities of that particular work product. And A is for the person who is going to approve the work product. S is the person who will be supporting for that work product. And I is the person who will be informed. So there sometimes some work products should be performed by the OEM and some work products should be performed by the supplier. So during the DIA discussion, we'll sit together and discuss who will do what, who will be responsible for the work product, who will be supporting. So all these things will be filled in this RASI chart. And next is how are we going to deliver the work product. We have 4 types of deliverables. One is full as deliverable, full at location, short as deliverable, and short at location. So if it is going to be full as deliverable, say suppose for example your safety, you will be performing the work product fully and you will be sending it to your customer. Full at location means that these work products you will not be sending it to your customer. The customer has to come to your location and he has to check it. Say for example all your requirements, how you derived all your functional safety requirements from your safety goal, how did you get into your TSC, then how did you get into your hardware software, then how did you export it to your testing, and how did you test it, and where all the test cases pass. So all this flow, the customer will have to come to your location and he to take a full review of it. So next one is short as deliverable. There are some work products wherein you will not have to deliver the whole work product. For example, if you're performing your HARA, you will not deliver the whole work product to your customer. You will have to just take the output of the HARA. That means you will only deliver the safety goals. So this is short as deliverable. And the next one is short as location. When the customer comes to your location, for some work products, he will not review everything. For example, if you take FMEA, he will not sit and check every function net, failure net, or every functions of failure. He might be interested only in the RPN levels maybe. So these kind of things are short at location. This is how you will be delivering it. And who sends to whom in the last, you have to mention it. This will be usually the responsible person who will be sending it to the person who is going to approve it. So this is what is present in the development interface agreement. So next, about the impact analysis, Prasneh will be taking you through.
So the impact analysis. So there is so main thing is that the function or the system requirements of the item can meet the product requirements. So just to give an example, that if they do you have a separate there is a special interface requirements to a sensor which could be fulfilled by the product to achieve a safety functionality, and this could be one of the item which is there as a new requirement. So whether it can be feasible inside the product requirements. So this is the main target for the impact analysis. So who is responsible for the impact analysis? The function integration manager. It can be named in different way. The system requirements engineer and the product manager. So the functions integration manager is responsible to check the impact on the functions. Functional requirements which is fulfilled by the product, then the system requirements engineer is responsible for the system architecture, whether it could receive, and the product manager, and it is supported by hardware, software, and safety engineers. What we do: document all the requirements, clarify unclear requirements, check feasibility of new requirements, evaluate the impact of all the new requirements. Yeah. And then we inform the analysis, or we share the analysis of outcome to the OEM on case-to-case basis. By this, we could identify that whether the product has to go for a modification, or the product could not meet the requirements and we have to go for a new development. And once we finish the condition that we could modify, okay, then or we could go for a new development, then we check regarding the functional requirements and we do the risk analysis of the functional requirements. And this will be taken by Supriya.
So yeah, now that we have the item definition, the hazard analysis and risk assessment will be performed on the vehicle level. So, and after the hazard analysis and risk assessment is performed, the output of the HARA is the safety goals or the top level safety requirements will be derived out of the HARA, and then we will be assigning ASIL ratings to all the safety goals. Again, here the responsible people are the safety managers from both the OEM side and the supplier side. So now how are we going to assign the ASIL levels for this? We have three parameters here, that is the severity, exposure and controllability. So all the tables for these three parameters are present in the part 3 of the ISO 26262. So based on these three parameters, we go to our ASIL table and checking where it comes under, we will derive our ASIL level for the particular safety goal. Yeah, moving to the next slide. Now, as I said, the OEM and the supplier will again have to sit together for this safety goal alignment also. Usually it is that the OEM have to perform the HARA on the vehicle level and send the safety goals to the supplier, wherein supplier has to analyze it. Or this is not the case most of the time. The OEM will ask the supplier to perform the hazard analysis most of the time, wherein in such cases the supplier will perform the HARA analysis and the OEM will act as a supporting person for this one. Or there can be another case wherein the OEM also has performed their HARA and have their safety goals, and the supplier has also performed HARA and have their safety goals. So in this case, both of the safety managers should sit together and map each and every safety goal and check if all the safety goals are covered and if all the ASIL levels are matching. So we should make sure that the ASIL levels are matching, and if there are some cases wherein the ASIL levels are not matching, then we have to decide upon what to do on this, or you have to change your ASIL levels, or you have to talk to your OEM and negotiate it. So these things you will discuss and you will agree upon what you are going to do. So this was about the safety goals, and the functional safety concept will be taken through Prasneh.
So right now that we know the safety goal at vehicle level, so is our internal is the supplier internal safety goal is aligned to the OEM, or if there is a need of a discussion, or is there is a need of clarification. So all these things has to be taken care by defining the final safety functional safety concept. So result of the hazard analysis has, I think, just to give a very short picture, results of the hazard analysis has been coming as safety goal, a multiple safety goal, and the functions, the safety goal is defined at vehicle level on some specific behavior, and all the functions which could contribute to that behavior is grouped towards that safety goal. And do all the functions is meeting that safety level which has been defined at the vehicle level risk analysis. So this is what exactly the functional safety concept has to be has to represent. So what is the objective? So to derive the functional safety requirements from the safety goal, which is in line with the vehicle architecture, to allocate the requirements to the primary architectural elements of the item or to an external measure. An example, a function has to be fulfilled by taking some kind of sensors. So it has to define which sensor at which tolerance level or at which ASIL level of the signal I expect to perform this function. So up to this elemental level, requirements has to be defined under functional safety concept. So the safety goals is which is refined by functional safety concept. So functional safety concept consists of functional safety requirements and functional safety architecture. And the responsible for this is function integration and project manager. Function integration project, sorry. So maybe there is an example which will be explained by Supriya.
So here, to explain the functional safety concept, I have taken an example of an airbag control unit. So I've taken one safety goal from this. The description of safety goal is unintended deployment of airbag shall be prevented while driving. Means while you're driving, suddenly the airbag should not deploy without any intention, unintendedly. So the ASIL level given for this is ASIL D, considering the severity, exposure, and controllability parameters. And here the fault tolerance time interval is given by the customer, which is usually greater than the sum of the diagnostic test interval and the fault reaction time. And this will be usually given by the OEM. And my safe state is I have to switch on the warning lamp if any fault is detected in the system. So now I'm deriving functional safety requirements from the safety goal. One of my functional safety requirement can be my airbag shall not be provided with firing current without the intention of the ACU. Means when my ACU is not intended to give firing current, it should not provide the airbag with the firing current to deploy. So the safety measure of this can be the safety integrity of the connection between the ACU and the airbag should be taken care of. And the ASIL level that I have given for this functional safety requirement is ASIL D, because if this requirement is violated, then it will directly violate my safety goal. So that is why I've given the same ASIL level as that of the safety goal. Okay. So this was a small example. And now that we have our functional safety concept, we will be moving on to the planning phase of the functional safety activities. So now, for deriving the project safety plan, we have to consider the inputs, that is the development interface agreement, the customer safety plan, and the project schedule. So we have to consider these three work products as the inputs, and while having these three in hand, the whole project team will have to sit together, wherein we have the project manager, the safety manager from the quality, the requirements engineer, the hardware project manager, software project manager, the tester, the function owners or the function PMs. So, and the functional safety manager has to sit together and decide upon, and they will come up with a project safety plan. This project safety plan will usually be present in your project plan. If it is not present in the project plan and you are making it separately, then you have to reference this in your project plan. And the activities that are present in the safety plan can include the implementation of your project safety activities. You have to define about the tailoring activities, the supporting processes, the verification, validation. You have to mention about your reviews, your audits, assessment, what are all the safety analysis that you're doing, what are the safety tools, what are the tools that you're using, and all the work products, and who is the person who is responsible to perform the work products. So all these things will be present in the project safety plan. Yeah, so moving on. The technical safety concept will be explained by Prasneh.
Safety concept of a special function. Say, for example, ABS, and towards. So, what are the signals needed for ABS? Function is defined by the functional safety concept. And what these signals has to fulfill and what the outcome towards the actuator has to be fulfilled inside the system has to be defined by the technical safety concept. And it has to be in line with the functional safety requirements. So functional safety requirements is defined by technical safety concept, and it will be also having technical safety requirements and technical safety architecture. And the problem, one of the problem will be that this is a function. The system, say for example, a function is realized by certain signals, and who made it realized is the system, and the inputs to realize that function could not be from only from inside the system. It could be from outside the system. And if the signals required to fulfill the safety requirements of the function is not available in the vehicle architecture, this will be the biggest challenge for the system engineer to define a adequate safety concept for the function. Here comes the negotiations and also the discussions how to solve along with the vehicle architecture. So I'm just giving an example, that's all. I mean, safety goals, the final refinement should be safety goals, which constitute a safety concept, constitute a technical safety concept, constitute to the component level of the system. Arriving to design concept and analyzing against safety metrics. So finally, we have a design concept available at the system level. And then we have to analyze and to meet the safety metrics. So we do the safety analysis for this. The objective of a safety analysis is that avoid and control dangerous failures of safety-related control equipment. Where it is mainly performed, it is performed at system architecture level. So what has to be avoided and what has to be controlled? Avoid systematic failures. So this can be by due to the design, development process, and manufacturing process. So this design process, development process, and manufacturing process has to be aligned and strictly to be within the state of the art. So this is what exactly that we, one thing that has been checked to avoid systematic failure. But on systematic failure during operation of the system, this is by implementing the technical measures during the product development. That is like by, for example, monitoring diagnostic functions, getting redundancy from hardware and software. All these things has been taken care. Defining the safety barrier before actuating a function. So all these things will be taken care by the design. And by doing this, with the architecture, we should be able to get into some figures. That is like talking about some fit rate, some RPN values, all these things. that has to be analyzed, and it has to be checked that whether the defined result of the analysis is meeting the ISO defined standards metrics, safety metrics. So the detail will be as per ISO will be explained by Supriya. Over to you.
Okay, so as per the ISO 26262, we have two safety analysis methods based, two safety analysis methods, and based on the ASIL level, it is described whether that particular analysis is recommended or not. So here, if we have a double plus, that means for that particular ASIL level, that analysis is highly recommended. And if it is a single plus, then it is just recommended. And if it is an O, that means it has no recommendation. So here we have the two analysis, that is the deductive analysis and the inductive analysis. As you can see, the inductive analysis is recommended for all the ASIL levels, wherein the deductive analysis is only highly recommended for ASIL C and D. So here the deductive analysis is a top-down approach wherein we know the effect and the cause is unknown. So we start from a safety goal for the faulty analysis, and we dig down to the base events. And the inputs for this is from the concept phase, we will give the FMEDA, and again the failure rate metrics from the FMEDA will be given to the faulty analysis. And again, the second one is the inductive analysis, which is the bottom up approach. Here we know the causes and the effect is unknown. So we go from the causes to the effects. So here from the system FMEA to the design FMEA, the severity is the input, and from the design FMEA to the system FMEA, we will be taking the occurrences. Yeah, moving on.
And once we finish the design FMEA, so we perform at the design level analysis and also at the system level analysis. Then the design is ready and implemented. And then we have to go for the execution of test. So objective is to raise the confidence on the implementation against safety requirements. And ISO recommends some test method. What all kinds of test has to be performed, on which ASIL what kind of test is mandatory, which ASIL what test is not mandatory, which environment the test has to be performed. So there are some recommendation. With the recommendation and the available infrastructure and available resources, we had to create the test method, which is adhering to the ISO. And then we have to make the plan, then the design, and test execution, and test completion. Mainly, we do have three tests: engineering test, design validation test, and product validation. So engineering test is kind of development test. It could be iterative test, and it doesn't have the developer decides the test environment and the test condition. In design validation, this is more related to the release of the product, release process, release of the stages, release of the software release, release of the system. And basically the test manager coordinates it. So he also coordinates and he also collects all the test results of system component and system test team. And product validation, it is on the production process. So this, in the development phase, engineering test and design validation is performed. So we will test planning against the safety requirements. So all the safety requirements test has been planned by using a test method which has been defined by the ISO 26262. And the test environment is defined, either vehicle test or could be hill test or sill test, and then test reports has been generated. Finally, the right part of the V is finished. Now we are entering up to the last part of the FSM cycle. So it is in development, so it is documenting. So creation of ISO 26262 conformal safety case. So we do have the work products which has been agreed in DIA. We also have a clear project plan and milestone which has been made. So both with the help of both, we have executed the V cycle. We have evidenced the work products related to each phase of development, and all the work products will be documented and linked in the safety case, and then finally the safety case document can be given to the OEM or the customer at the end of the development. And then coming to the safety confirmation measures. So we finished the V model. Now we also have to have a check that whether we did really adhere to the ISO 26262 at each phase, not making a final audit. So there are intermediate audits performed. This is also one audits or reviews or inspections performed in between, and this will be explained by Supriya.
So the confirmation measures according to the ISO 26262 are we have the reviews, the assessments, and the audits. The reviews are basically performed for every work product, and the assessments, as Prasneh explained in the V cycle, we will have it periodically. So for every phase, depending upon the project maturity, we perform the FSM 0 to FSM 4 assessments, and the audit. This is usually performed in the end phase of the project, or if your customer is requesting, you can also perform it in between also. So moving to the next slide. So these are for the FSM reviews. So here we'll be performing periodic reviews for all the work product at different phases to check if the safety maturity is achieved or not. So in this review, we will be checking the aspects like the planning, execution, completeness, and correctness of the work products. And this evaluation will be based on the methods and tools, and each review is performed will be having a checklist, and all the things that were captured during the review will be documented neatly. So, and the responsible person for this reviews will also be the safety manager or the assessor. So these are the different types of verification review methods. We have screening method, walkthrough method, inspection method, and the formal verification method. The screening is recommended for ASIL A and QM. Here in this screening, meeting may not be necessary, just a comment technique review method is present, wherein the person who has prepared the work product will be mailing it to the person who will be assessing it, and there again the person who will assess it will check and he will mention some review comments and he will mail it back to him. So this is screening. And next we have the walkthrough method, wherein it is recommended for ASIL A. Here the meeting is necessary, and in the meeting the person who is the author or the person who has developed the work product will explain a step by step to the person who is assessing it, and in this process the assessor will give some suggestions or improvement methods, and this will be taken and again it will be refined. In the inspection method, it is again recommended for ASIL B, SC, and D. It will follow a multi-step process wherein you have your planning, introduction to the preparation, inspection meetings, error analysis, rework, and acceptance. The last one is the formal verification method, which is recommended for ASIL C and D. So here we'll be following the checklist method. and everything will be documented in checklists. And here we are also taking according to the ISO standards, we will have to present the evidences which are textual, diagrammatical representation, or any language evidence are there. We should be able to show it. So moving on, the assessments will be explained by Prasneh.
So functional safety assessment is being performed to check the correctness of execution on each and every phase of the functional safety development. So FSM assessor shall be sufficiently trained and experienced with the product and applied technology and relevant requirements of the project being assessed. FSM assessor shall also have a level of independence required by ISO 26262 depending on the ASIL classification of the safety goals that are subject to the assessment. That means that FSM assessor should not be a part of the development team. So I will just quickly go through a kind of FSM assessment. I think we have been we have already discussed that there are 5 level assessment. One is FSM 0 on the concept phase, FSM 1 on the design phase, FSM 2 on the test concept phase, FSM 3 on the validation phase, and FSM 4 on the documentation of the complete safety requirements. So the main we have around 8 topics or 8 areas need to be assessed. So the safety management, it's coming into the design phase mainly, which is application of the organization safety culture and supporting process is assessed here. The roles, responsibilities, and all these things in the process, and the whether the tailoring has been made or tailoring is documented for the safety safety cycle. This is also assessed. Yeah, all related to the process planning, project safety plan, and things like that. Then safety activities during the concept phase. So this is mainly on concept phase. So when you see that 0.1 and 0.2 means a 2 level of assessment. So it could be first 0.1 would be item definition, hazard analysis, and all, and 0.2 could be the safety concept, functional safety concept. It can be also merged to one assessment at FSM 0, or to a detail if the safety criticality of the system is to the high level. That means the integrity level is ASIL D, and then always recommends to have 2 phases of assessment in that case. Safety activities of system development, as I already, system development is on the development side. So it will be, again, planning of system development, integration, and validation of system. Technical safety concept is the major part in FSM 1.1. Then the test concept definition for the system. Yeah, this is also taken care here. Then hardware development and software development. This commonly I could just explain in. So it has been the FSM 2.3, that is the component development, as we have already discussed, of the system component development and test concepts will be assessed. So what is the component development concept and the test concept for this component? Then item integration always talks about on the final test concept of the components, and also the test validation reports of the system. And then validation and the release is again the final reports, including the vehicle test reports for the release for production. And the planning of production and maintenance is the the assessment. This assessment is also included in FSM because this is also will be covering the planning for the production and also the controlling measures. So maybe I think we will explain more on the production side. And all these has been taken into the final documentation has been maintained, and the final assessment will be on FSM4 assessment. And with this assessment, it is confirmed that it will be having the reports from, it will be having the links of all the assessments, all the status of the assessment, and finally the assessor will confirm, yes, the development has adhered to ISO 26262 process, design, and also the methods. So audits will be explained by Supriya.
Yeah. So coming to the audits, as I said, the audits will be performed usually at the end phase of the project, or if your customer has requested for an additional audit in between between the development of your project, then this also can be taken care. So the main objective of the audit is to check the process definition and the process adherence. So, and the projects that are fulfilling ASIL C and ASIL D, the audits are mandatory. Again, the audits can be internal also and external also. The internal audits, we can have IATF audits wherein they will check your internal process definition, and for FSM they will check basically the FMEA in the internal IATF audit, and the external audits will usually be taken care by the customer, or a third party person will come and do the auditing for the project. Yeah. So now developing with qualified tools. So we have to make sure that all the tools that we are using in our project are qualified tools. So here we have tool classification and qualification. So firstly, we need to classify our tools. So after the classification, if required, then the tool has to be qualified. So firstly, the tool classification includes these three things, wherein we have the determination of the tool impact on the development on the developed item, and next we have determination of tool error detection, then we have determination of the tool confidence level. And after the classification, if the tool confidence level is greater than 1, then we need to qualify the tools. So moving to the next slide. So here this is for the tool impact and the tool error detection. So for the tool impact, we are checking for the possibility of the malfunction of the tool, wherein it can introduce some errors or it will fail to detect some errors. So if there are no such possibilities in the tool, then we can select it as TI1, and for all other cases it will be given as TI2. Now going to the tool error detection. Now, if the confidence in the measures that prevent the tool from malfunctioning, if we have high degree of confidence that the malfunction is prevented by the tool, then we can select TD1. And if there is medium degree of confidence, then TD2 will be selected, and in all other cases, TD3 will be selected. So moving to the next slide. So here, this is the determination of the tool confidence level. So based on the TI and TD values, we will check the tool confidence TCL value. For example, if my tool impact is TI1 and tool error detection is TD1, then it will be given as TCL1. Otherwise, if it is TI2 and my tool error detection is TD2, then it will be classified as TCL2. Or if tool impact is TI2 and the tool error detection is TD3, it will be taken as TCL3. Here for TCL1, the tool qualification is not required. Only if the value of the TCL is greater than 1, that is for the TCL2 and TCL3, the tool qualification is required. So this is mentioned in the part 8 of the ISO 26262 methods, wherein the qualification of the software tools for TCL3 and TCL2 is defined. So these are the methods that we have to follow according to the ISO 26262 for the qualification of the tools.
Okay,
so the FSM in production will be explained by Prasneh.
So now we have completed the environment that we used to develop. So we completed these the V cycle and also the conformance measures. So now let's just see that once the development is finished, now the production has to start. So do production is having some relation. So FSM in production. So once we finish the product development, it is going for the production. So what are the main work products from the production, which is related to FSM? So the main work products is a production plan, is production control plan, control measures report, specification of requirements on producibility, assessment report on the production capability. So what is a production plan? Is assembly instructions, work instructions, the skill set of the employees which is there in the production plan, producing a safety critical component, competency metrics thing, training metrics, then traceability measures, process failures and their effects. So PFMEA failures occurring during production. So all these things are a part of this production plan. Yeah. So this also gets input from the development. So I will just explain in the next slide for that. And production control plan. Okay, this is just for controlling that we are just making the plan. So how many things has to be produced and which line has to start and all these things. Start making these the safety critical product. Control measures report is a test report of these production control measures. And spec of requirements on producibility. So this constitute drawings, industrialization meetings, so build quality report, the PFMEA, all these things are like what are the spec for the producibility. So when you say about the spec for requirements of producibility is that if you are just assembling a product inside the production plant, and if the assembling of the component, is it related to safety? And if that is this, is it a safety, then we have to write the test spec like before, after finishing the assembly, then further test has to be performed and ensure that there is no false assembly. So this is also coming as a part of PFMEA. So spec will define the PFMEA, this process FMEA, and assessment report on production capability. So this gives the how many such kind of safety critical products can be manufactured at a given point of time, something like that. And PPAP, yeah, so product validation part. So let us see development, production, and operation. So I just make it short. So from the development, we are just doing FMEA. Just to give you an example, I think there are other special characters also. We are doing an FMEA, and we are doing a system FMEA, we have doing design FMEA, and finally we are just getting into the metrics of the occurrence rate. Occurrence can happen from that particular component, and occurrence means a failure occurrence. So the failure occurrence, if a sensor is getting integrated into a system, so that there is a failure, a particular failure occurrence for that particular sensor. And if it is getting integrated, assembled into a system, then there is also a possibility that there is a failure, there could be a failure that can happen in that in the assembly side. So that the failure on the possibility at the assembly plus the failure of that component give the total occurrence rate of towards the system. But if we don't wish to make actually if the criticality of that particular component is very high, so that which is mapped to the high severity safety level, then that severity from the top function level has to be cascaded to the system, has to be cascaded to the component, has to be cascaded to the production. And the PFMEA has to adapt towards that. So the detection mechanism of a fault assembly has to be ensured in the production line so that there is very less chance of making a false assembly. And this is how it has been related. So this traceability has to be established in the production. So for the ISO, then we have safety requirements, product drawings, DFMEA. So we have special characteristics, which could be the severity cascaded from the top, giving to the assembly instructions, production plans, and also the PFMEA, which will be given as a spec to the PFMEA, and then final occurrence rate, that the failure occurrence that could happen because of, even though we implement a lot of detection mechanism, a lot of failure-free mechanism, still there is a possibility of a failure. So that minor failure also has been given back to the DFMEA and then to the system FMEA. I'm just giving as a FMEA as a background, so that's the reason I'm just taking an example. And this has to be ensured that whether this flow has to be ensured by the plant quality and the safety manager. So they should have a reporting structure for optimizing the plan. And also there should be an escalation method that has to be established to adhere to the functional safety there. In case if there is a if there is a higher fit rate identified, that means like fit due to occurrence rate is high, identified at the plant, then there should be an escalation mechanism which has to be shared and discussed with the development engineers. Yeah. So all the AD analysis lessons learned should be shared with the safety analyst in the development team. And by doing all these things, we made it possible in developing a safety system which is functionally safe. By defining the system, analyzing the risk on hazards, aligning to safety requirements and meeting vehicle architecture, plan to meet the project milestones, finally, design to meet the state of the architecture, tested without compromise, produced with quality and adhering to safety. So we made products functionally safe. So that's it from our side. And thank you very much for listening. And now the floor is for questions.
I have one doubt actually. This about this audit. So if this phase of the project is very initial, like strategy development and going on, what could be the audits? Even now we have some external audit planned, but the project phase is initial, where strategy development for different testing, like unit integration, is going on. So what could be the checkpoints for that phase?
Um, Probably the checkpoints could be on the on your plan and the process, because you are not
Okay.
entered into the architecture, right?
Yeah. Okay. And you mentioned it's based. Is this
Hello?
checklist? Yeah. Is this checklist is something everyone can access, or it's only for the auditors?
Regarding the audit checklist or inspection
Yeah.
checklist,
Audit checklist.
I think it can be prepared by the external auditor. It can be either prepared by the external auditor, or it can be prepared inside the organization as an internal audit checkpoints. So both the ways.
Okay. Okay. It's not in any ISO. This standard. It's not part of that.
Yeah, but
Like
if
any of the parts.
yeah, this I had to check into details if we have a clear template for the checklist, and maybe I may have to come back to you. But as of now,
Okay.
I think this audit is usually performed by the customers
Hmm.
and also by
Okay.
the external agencies.
Yeah. And this tool classification, at what phase we have to go for that tool classification and qualification?
We have to go start when we start the process. When we set up the process itself, the tools has to be classified, because the moment we start the development, we need to use the tools.
Yeah.
So ideally, it has to start like that, uh, and
Okay.
it could be also tailored, like in case it can just qualify until the concept phase is finished. When we can, it can go in parallel.
Okay. Yeah. Thank you.
Hello, can you hear me?
Yes.
I just wanted to ask, in the technical safety concept you had, concept means it is having a architecture plus the requirements, right? That is
Yes.
what you
Yes.
had given. So
Yes.
what is that artifacts that used, or when we should be ready with that kind of to be facing the audit, or you mean to say what is that expected from that technical safety concept as such?
It will be the technical safety requirements and its traceability towards the architecture.
So finally, it's anyway, we will be having some kind of a tool to have that requirements and some kind of a tool to have a traceability that
Yes.
should be good enough to say that we have from the requirement to the architecture, we have a traceability, and this is good enough to prove that it is a technical safety concept is done.
Yes, technical safety concept is done, which fulfills the safety level, safety integrity level uh, of that requirement. Say, for example, if you have an upward traceability to the functional safety requirement, SLD, and in your system level requirements, you are not fulfilling SLB, and there is a mismatch. That
Okay.
means that the audit, it could go as an NC. If that is the case, and if it is because of some issues with the vehicle architecture, this has to be documented and has to be evidenced and agreed between both.
Okay. Thank you.
This could happen in practically sometimes.
And the second question I had was, you had given an example of a airbag control unit and the safe state.
Yeah.
The safe state.
Probably Kiran, right? Maybe my colleague Supriya could take it up because she's from that.
The safe state was yes.
Give an indication as a lamp, you said, because here the airbag is already unintendedly operated and it has already blocked the driver. So hence indicating through a lamp could not be a safe state right there.
No. It will if there is any fault that is detected in the system. So initially only it will warn using the warning lamp. It will.
No, that is where I wanted to know what is the definition of a safe state. Safe state is a condition where even if the failure occurs, how will I control it or how will I manage it? Am I right in that definition?
Yeah, so initially, if there is any fault that is found in your system and you warn your driver that there is some fault in your airbag, so then the driver can switch off, or for example, there are some switches wherein you can disable airbags. So by using that switch, the driver can disable the airbags so that it won't be deployed.
Or in the other case, like the safe state is that, okay, a driver is informed that the airbag will not work. And he should avoid, he should go to the garage. That means that you are expected to go get a malfunction from the system.
Yes, right.
Okay, thank you.
Yeah. This is okay. Go ahead.
Please go ahead. Sorry.
Okay. This is Priya Sloka. I have a question on slide number 58.
Okay, just a moment. Slide number 58. Okay, it's regarding the assessment.
Could you pick it up or?
This one, right?
Yes. So here, just looks like this E1, E2, maybe it has come. This it was part of Annexure E in the older standard. And 2018, I think this is not there actually, this annexure. So that's again not the point. Just wanted to understand the FSM 1-2 or 0-1 or 0-2. Is it your internal?
No. Actually, this
how
is
you are coming at these numbers.
Yeah. I'll just tell you this one. Actually, if you have FSM 0 is concept, right? FSM 0 is concept. So a concept, what all things it is having? Item definition, hazard analysis, and risk assessment, functional safety concept, right? And then could be dependency on the item safety concept with other system functions. So interfaces with external measures, all these things are coming here. So we categorize this into two different phases. Like 0.1 is like, okay, we just look into only item definition and hazard analysis. And 0.2 will be, the assessment will be on the, mainly on the functional safety concept, like that.
Okay, so if you take 2-4, so that is concept. Sorry, that is okay. 2 is what actually?
2-4. 2 is component. Concept design, and 2 is component design.
Okay, so maybe just request you maybe if you can bring a little bit matrix. It will be easy. Even I'm into this 262, but I find it a little bit difficult to follow up. So
okay,
yeah,
okay, fine. So only thing is that just the intention is that only just what all activities just inside the FSM assessment. Yeah, so we We could just go with the flow. But when we just want to assess like safety management, okay, safety management assessment will be performed in the development phase, the development start. And then we call safety activities of concept will be always done in the concept phase. Safety activities of system development will be executed at the design phase and also the test concept phase.
I understand your
So I just want to, because when we say safety activities against the system, so this
Sure.
okay, I understood. I took your I take your feedback. Thanks.
Yeah, I have another question now. So one of the slides you have shown that different kind of testing, and I don't remember exactly what are the slide, and the kind of test planning in different different like unit testing, integration testing, hill, sale, and all those things are there. It's one portion of a slide. But the question, what I'm trying to ask you, I think this is this.
Yeah.
From you, it may be a little bit open-ended question, but from your experience, how you plan those, which of the, phases, how you would, do those kind of testing. So how does the test pyramid or test strategy goes from your experience point of view? So a little bit open-ended, but I don't want to hear from you how you plan.
No, I think see. You mean to say that we make it mandatory for certain
why I'm asking this question, sometime it will be a duplication you can do in system, sometime you can do in unit test. As a test architect, you plan some of the tests you would do in the upper layer, some of the tests you do lower layer, so that you don't duplicate a lot of effort. The question is more towards how you plan so that
since we integrated inside the V model, as I start with, so the test plan for this test method has been defined as an integral part of our process. Okay, then we identify, say for example, we do interface test for a QM signal. We don't test it in. We did not have to test it at vehicle level, probably. For say for example, steering wheel angle sensor interface integration test to the electronic brake system. Okay, this is a very high relevant integrity level component interface which is coming to us, that we don't want to compromise, so that we will mandatorily test without any compromise. So that is how.
So thank you very much, Prasneh and Supriya. I really appreciate. This is one of the very good 2626 training I've attended in past 6 months. I really appreciate. Thank you all.
Thank you.
Thank you.